All right. Hello. As many of you have seen, I made the test available for now. You can go in and see your responses, see the items you missed, and also see video explanations for each question. Please be circumspect in your use of that information. There are a handful of stragglers that have not yet completed the exam, so I do not want you to make things widely disseminated. Please do not post them on the internet and all of those things. I've had a few questions already about a particular item where an answer looks right, but points weren't awarded. This is new to me. I will take a look at it after class. I will make sure everything's okay. It's very easy for me to go in after the fact and correct those kinds of mistakes. So have no fear. I think that probably happened to quite a few of you, and I apologize. Any questions about that? People are saying that the screen share is blurry. Okay. There, I stopped screen sharing. Now it's not blurry. Take that. Is that any better? I have to restart the chat function. Okay, are we a little bit better on blurry, folks at home? Okay, so a lot of concern on the chat. Perhaps you didn't hear. There's some concern about folks getting question 16 right, but no points on it. That's some kind of glitch that I'm not aware of. I will fix that after class, so do not worry. It will be okay. All right. I wanted to give a little bit more background on hyperconjugation because I think it's kind of a difficult concept, and though it's not hugely important for what we're talking about, it will be really important in the future. And some of you who've asked me questions in office hours, this may be a bit of a repeat, and hopefully we won't spend too much time on it. But hyperconjugation, what is it, and why should we care? Well, let's begin with a simple carbocation and positive charge on the carbon. And based on what we've discussed so far, you would have concluded that the LUMO for this molecule was the empty p orbital on the positively charged carbon. And if that's a confusing conclusion to you, you need to go back and look at the MO theory study guide to review how we came to that conclusion. Now, if you think about the reactivity of this molecule, if a nucleophile were to come in and react with our carbocation, you would predict that it would do so at the positively charged carbon. And in fact, we do observe products of this kind where we have a new sigma bond where we have the nucleophile attack the positively charged carbon. But we also observe a product like that. And the only way to rationalize that is by imagining that the nucleophile could also attack the proton that's adjacent to the positive charge. It is probably confusing to you right now to see totally where this alkene product came from. For now, don't worry about these arrows. What you need to worry about is just the background that I've given you, that there's evidence that a nucleophile can attack not only where we think the LUMO is, but also on an adjacent atom. Okay? And since I've told you everything in OChem is HOMO attacks LUMO, that should make you feel a little bit uncomfortable because, okay, now how do we know if it's going to attack the positively charged carbon versus the hydrogen? And we'll talk about that in chapter 7. I will point out that our decision that the LUMO was going to be the p orbital for this molecule came from our hybrid MO theory, valence bond theory approach, where we still consider bonds to be two electrons localized between two atoms, but we imagine that the bonds here, for example, are in a carbon-carbon sigma bonding orbital, and then there's an associated empty anti-bonding orbital that's really high in energy. All right. So it turns out you can get a decent explanation for why the nucleophile can attack that adjacent hydrogen from a pure molecular MO theory approach. And you can actually calculate what the LUMO of the molecule is. Now, what do we mean by a pure MO theory approach? Well, remember I said that for the most part, this is going to be too complicated and confusing for what we want to do in this class. As a brief reminder, remember that we said you could generate a bonding orbital for methane by combining all 4 1s orbitals, one from each hydrogen, with the 2s orbital on carbon to get a delocalized orbital that looks like this, spread over the whole molecule. Recall that we said that in pure MO theory, you don't even worry about bonds anymore. You instead make molecular orbitals that are delocalized. And we said that's useful, but it's going to be a little too complicated and unnecessary for most of the things that we're going to do. With this exception, if you do the MO theory calculations for this carbocation, and I used to could not say that I had actually done them, but I did them recently and have confirmed that this is true. One of the interesting, one of the interesting things you see is that the LUMO does indeed look like an empty p orbital on the positively charged carbon, but interestingly enough, there's some of the LUMO out on those adjacent carbon-hydrogen bonds. And that's convenient, or perhaps a more realistic view of what the LUMO is, because now it's more reasonable for a nucleophile to have to decide whether it's going to attack the LUMO either at the carbon or at the hydrogen. All right? So the point is that the MO theory approach gives us an answer that helps us explain this observation that we made at the beginning. Now, we're going to need some kind of tool or bridge to get from our simple view of what the LUMO is to a more realistic or useful view of what the LUMO is. And that bridge is going to be hyperconjugation. All right, so where do we get, how do we get there? How do we get this idea that the LUMO spreads out? Well, what we're going to do is go back to our original days of combining individual orbitals together to make a bonding orbital and an anti-bonding orbital. For example, do you recall that when we wanted to make a bond between two carbons, let's maybe just do ethane, we said that this sigma bond came from overlap of an sp3 orbital on carbon with an sp3 orbital on the other carbon. And MO theory math requires us to take the plus combination and the minus combination. The plus combination just really involves taking the two sp orbitals like this and overlapping them, and you get a bonding orbital that has most of its electron density in between the two atoms, and then we did the minus combination to generate the anti-bonding orbital. We can still use that approach with orbitals other than atomic orbitals. So if I were to look at this carbocation that we've drawn here, and if I were to look down the carbon-carbon bond in a sort of Newman projection format, one of the things I would notice is that the carbon-hydrogen bond on that adjacent carbon is lined up with, side to side lined up with, the empty p orbital on the carbon that's positively charged. You see where I'm getting this from? We're looking down this bond and we see that the carbon-hydrogen bond lines up with the empty p orbital. And in fact, if we redraw the molecule from the side, one of the conclusions that we can make is that that filled carbon-hydrogen sigma bonding orbital overlaps with, in sort of side-to-side fashion, overlaps with the p orbital on the positively charged carbon. So what we're going to do is we're going to mix those two together, plus or minus, and doing that is going to give us two new MOs. One of them is going to be bonding and the other one is going to be anti-bonding. This is exactly the same as we would have done with an sp3 orbital on one carbon and an sp3 orbital on the other carbon to make a new sigma bonding orbital. When you mix two orbitals together, you get one that's lower in energy and the other that's higher in energy. And if you only have two electrons, you get to populate the lower energy bonding orbital and leave the upper higher energy anti-bonding orbital empty. Okay, with me so far? So let's see what we get from the plus combination. Actually, the orbital we would get would look very much like what we've drawn. So sigma CH plus 2p is probably going to look like this. It's going to still look maybe mostly like a carbon-hydrogen bond, only some of that orbital is going to be spread out in this direction. All right. And the new orbital we form is going to look almost like it has a little bit of pi type character. Almost like there's a pseudo pi bond between those two atoms. It's not a complete pi bond. All we're saying is that the electrons in this carbon-hydrogen bond are partially delocalized into the positively charged carbon. What is the out-of-phase combination going to be, or rather the minus combination? Well, it should actually look like mostly an empty p orbital, but with a little bit of orbital out on the adjacent hydrogen, and actually, because this is the minus combination, they have to be out of phase. Okay? That looks a whole awful lot like what we got when we combined two p orbitals side by side to get a pi and a pi star. All right? So why don't we consider this to be a full double bond, a full pi bond? Well, it has to do with the fact that when we make a pi bond by overlapping two p orbitals together, the starting orbitals are close together in energy, so that the pi bond can move down quite low and the pi star can move up quite higher. When you mix together two orbitals that are not equal in energy, as is the case here, a carbon-hydrogen sigma bonding orbital is much lower in energy than an empty 2p, then the amount of mixing isn't quite as stabilizing. So this energy difference is small. It is much smaller than you would predict for a regular bond. Okay, it's about maybe 100 times 100 times smaller than the stabilization you would get from a regular bond. But it's enough that the electrons get to move lower in energy. Now, it's true that the antibonding orbital moves higher in energy, but who cares? It's empty, right? And so this effect we call hyperconjugation, because if you look at what we concluded from what happens to the p orbital, it spreads out a little bit onto the adjacent atom. That starts to look like the answer we get from the pure MO theory approach. Okay? Now, I don't really care that you go through it at that level of detail, but I do want you to be able to look at a structure like this and say, hey, I've got adjacent sigma bonds, and if they line up with and overlap side to side with that empty p orbital, the electrons in that sigma bond are going to spread out a little bit towards the p orbital, and the p orbital is going to spread out a little bit onto that hydrogen. Yeah?
Does the sigma MPP orbital combination have a specific name?
Does it have a specific name? No. We would, although I suppose we would guess it's something like a pi type orbital. And if you think about, I mean, look at this. If you think about what that combination looks like, it looks a lot like a pi bond. And in fact, we said one of the products would be a molecule with a pi bond there. And all you got to do to get there is strip the proton off, and then those electrons can go completely into a pi bond between the two atoms. So again, what do I want you to think about when you have an empty orbital adjacent to a filled orbital? Think about if the filled orbital can line up with the empty orbital side to side, you can stabilize the electrons in the filled orbital by allowing them to delocalize a little bit towards the empty orbital. And you're also going to spread out the empty orbital and have it delocalize a little bit onto the adjacent sigma bond. So a question from the chat: could you say that the empty p orbital and the hydrogen are eclipsed? Yes, and they overlap side to side. And the reason we've got, in this case, the LUMO spread out onto all of those CH bonds is because they all can line up with the empty p orbital. We were considering them one at a time. The pure MO theory approach allows us to consider them all simultaneously. For us, it will be enough for you to realize that some of the LUMO is on that adjacent carbon-hydrogen bond. Now, there's tons more examples where that's going to be the case, but for what we were talking about last time, we were simply worrying about conformations. And we said that the staggered conformation was more stable than the eclipsed conformation, because in the staggered conformation, a proton on one side, the sigma bonding orbital for that proton on one of our carbon atoms, is anti to a proton on the other atom. And because of the structure of what a sigma star is, that means most of the sigma star is actually going to be lined up with and overlap in a side-to-side fashion with the filled sigma bonding orbital. Here's the electrons in that orbital, a filled carbon-hydrogen sigma bonding orbital with an empty carbon-hydrogen sigma star. So effectively what we would be doing here is mixing a filled carbon-hydrogen sigma orbital with an empty carbon-hydrogen sigma star on the other atom. Now, I don't care. We're not going to worry about what the resulting new molecular orbitals look like. All we're going to care about is the fact that if I mix a higher energy sigma star with a lower energy sigma, I get one new MO that's lower in energy, and I get one new MO that's a little bit higher in energy. And because only one of my two orbitals that I began with is filled, I only fill the more stable MO1, and this is a favorable stabilizing effect. Okay? So that's the reason the staggered conformation is more stable. And if you think about how many hydrogens are in ethane, there are 6 of them. So we could calculate how much one of these interactions was worth. Last time we said that the staggered conformation was about 3 kilocalories per mole more stable than the eclipsed. And if there are 6 of these sigma plus sigma star interactions, that'd be about a half a kilocalorie per mole per sigma to sigma star interaction. You can use this same explanation for why the eclipsed conformation is so bad. The eclipsed conformation involves a filled sigma on one carbon overlapping with a filled sigma on the adjacent carbon. And you might think, well, hold on here, sigma bonding orbitals are close in energy, so wouldn't we expect to be able to make a really stable MO1 and then a high energy MO2? And I say, yep, but you've got 4 electrons here instead of 2. That means you fill the lower energy MO1, you also fill the higher energy MO2. This distance, the MO2 is larger in magnitude. The destabilization of MO2 is larger in magnitude than the stabilization of MO1. And so you've just created a very unfavorable situation. You've moved the electrons in the molecule higher in energy just by virtue of having them eclipsed. We call this, as I think I mentioned last time, closed shell repulsion, and it's the same reason why you don't take 2 helium atoms and make a bond with them. Because sure, you could make a bonding MO and an anti-bonding MO, but each helium comes with 2 electrons. You populate both, there's no benefit to bonding at all. All right, yes?
Because you're partially filling an anti-bonding orbital in the example just above, does that mean that that's weakening does that mean that's weakening that carbon-hydrogen bond?
It's a good question. Does that mean you're weakening the carbon-hydrogen bond? Overall, these electrons are moving lower in energy by delocalizing, and we're sort of stepping away from the concept of a localized bond in that case. But yes, you would predict this hydrogen to sort of be held less tightly because its electrons are no longer, the electrons from that bond are no longer localized there. And that's actually why, one of the reasons why it's easy for a nucleophile to remove the proton instead of just attack the carbon. One other thing that may or may not help you, the term hyperconjugation first came about because of people considering a so-called no-bond resonance structure where you would move the sigma bond between carbon and hydrogen down to make a complete pi bond, and then the proton would be positively charged. Without moving atoms, and you may say, hold on, that's bad, you just took electrons away from hydrogen, and I agree, it's a minor contributor, but it does give you the gist of LUMO being on this proton, and probably that proton being more acidic than you would expect for an average proton. So on the chat, someone says, how do we know whether there will be 4 electrons or not? Well, if favorable hyperconjugation situations will always involve a filled orbital with an empty orbital, all right? So look for sigma bonding orbitals adjacent to empty p orbitals or sigma stars and then being able to line up. Look for lone pairs adjacent to sigma stars or pi stars or empty p orbitals. all of these are opportunities for hyperconjugation to occur. All right, so it's not clear what kind of crazy question I could ask about this other than why is the staggered conformation more stable than the eclipsed conformation? And, you know, oh, I'm going to choose the answer that has hyperconjugation in it, and you'll probably be right. So not that useful to memorize things, but in the future, you're going to be predicting whether things can react with each other and being able to reason through what we've talked about to imagine where the LUMO is and to use that to predict the parts of the molecule that are reactive is going to be really important. So this just happens to be a convenient time to introduce hyperconjugation. Any other questions on that? Yeah.
So back up at the top, where it's either a second carbon or the hydrogen, is one more likely than the other?
Is one more likely than another? For this intermediate that's positively charged, probably not. When we have a reaction with an intermediate like this, we're going to always observe, at least we're going to be ready to observe both potential products. Yeah. And there are other situations that resemble this where it will go one way versus the other, and we'll learn how to think our way through that. All right. There's so much more we could say about that, but probably we should move on. So ethane is boring. You've been asking for quite some time, what if we replace one of those hydrogens with something bigger that's not hydrogen? All right, so let's do that. We'll choose butane for now, which is only slightly less boring than ethane. Again, let's draw the Newman projection. I'm speeding up, so I'm foregoing the Sith eyes. It's really killing me, but sometimes we all have to make sacrifices for the greater good. So from our perspective, looking down the carbon-carbon bond between, just for the sake of our discussion, 1, 2, 3, 4, between carbons 2 and 3, we would see the methyl group on carbon 2 pointing up to the top of the page. We would see the carbon-hydrogen bonds of carbon 2, one coming out of the page and one going back into the page. In the back, we would see a CH3 group anti to the CH3 group on carbon 2. We'd also see a proton here and a proton there. You should be good at drawing Newman projections. If you're not, you may need to practice with a model set. Being able to visualize molecules in 3D to go backwards and forwards from here to here is going to be really important in drawing conclusions. We're going to focus on the dihedral angle between the two methyl groups. Right now it's 180 degrees, and we'll call this an anti-conformation. We won't worry about the eclipsed conformations. You should see that probably if we rotate this front carbon by 60 degrees, we'd have a situation where methyls were eclipsed with hydrogens. And if we kept rotating, we could have a situation where the methyls were eclipsed with each other. Which do you think is worse, methyls eclipsed with hydrogens or methyls eclipsed with each other? With each other, yeah, exactly. But let's not focus on the eclipse conformations, which are going to be high energy barriers. Let's just rotate. And because we feel bad that we rotated clockwise last time and the poor counterclockwise direction felt sad and underused, let's rotate counterclockwise by 120 degrees. Take the methyl group in the front. And in doing so, we would generate the following conformation. We'll keep the methyl group in the back at the same position. Now the dihedral angle between the two methyl groups is 60 degrees. Now they are gauche to each other. And that should be somewhat, what do you predict? Is the gauche conformation going to be more or less stable or the same as the anti-conformation? Less, okay, right. Why? Because it is, but no, seriously, why? Steric strain, that's a new term, or steric repulsion. What do we mean by that? Torsional strain, yeah, what do we mean by that? Let me draw the this gauche conformation as we would see it from the side. And this time I'm going to draw out the carbon-hydrogen bonds. I believe in the way we have done things here that the methyl group would be pointing back into the page and the hydrogen would be here. Steric repulsion or steric strain happens anytime you have groups that get within touching distance from each other, right? We talked above about closed shell repulsion, and this is a different thing. You basically have electrons from these bonds, and if they get too close to the electrons from the bonds from the methyl group over there, they repel each other. It's just electrostatic repulsion or Coulombic repulsion. And that makes this arrangement quite a bit less stable than the anti-arrangement. And because I don't believe in memorizing numbers, I don't remember what that number is, though we can look it up and then maybe I have it somewhere. Yeah. But probably I don't care what the number is. Yep, still don't care. Actually couldn't find it, so it's convenient that I don't care. But yeah, the anti-conformation is more stable. The gauche conformation is less stable. Okay. And of course, if we rotated another 60 degrees, we would come to another gauche conformation where this time, I meant 120, sorry about that. We would come to another gauche conformation, this time with the methyl group on carbon 2 in the front on the right side of the methyl group in the back on carbon 3. So steric repulsion, and it generates what's called torsional strain. What do we mean by all of that? It simply reflects the fact that some staggered conformations are more stable than others, and some eclipse conformations are less stable than others. All right, so I want to draw an energy diagram, but before we do that, maybe I'll just pause for questions. Anything? Yeah?
So does the torsional strain have to do with like bond overlap?
Does the torsional strain have to do with bond overlap? The eclipse stuff definitely does. In terms of why the gauche conformations are less stable than the anti-conformation, our explanation for that will just be steric repulsion or electron-electron repulsion from having those two groups close to each other. Okay. Yeah. Does this change the bond angle on the atoms? That's actually a good question. I guess the word I was looking for was not actually. Like, I don't mean to distinguish this question was actually interesting as the others were not. No, they're all interesting. So that is a good question. Sometimes bond angles in a molecule will distort themselves to relieve steric strain. I can't think of a specific example of that, but it's a well-known effect in organic molecules. Others? Okay. So for the sake of our discussion, let's call this one at the top the anti-conformation. Let's call the next one gauche 1 and gauche 2. Actually, people will call this gauche plus or gauche minus, depending on whether the methyl group in the front is on the right hand or the left hand side of the methyl group in the back, and I don't, as I've said before, know or care about the sign convention. All right, so if we put energy on this axis, and then if we put dihedral angle on this axis between the two methyl groups, and let's say this is the anti-conformation, we won't put numbers on the dihedral angles, we'll just note things by their abbreviations. We expect the anti-conformation to be more stable, and then we expect the two gauche conformations to be identical in stability, but less stable than the anti-conformation. And you know what, actually, since I have the awesome power of copy and paste, we'll just shrink those down to remind ourselves what they look like. Why am I wasting time on this? Well, when you're the professor, you can waste time on pretty pictures that you like. That's kind of like telling your kids because I said so. It doesn't work. All right. So let's actually talk real briefly. Let's see. About getting from anti-conformation to gauche conformation 1. Zooming in on there, as we rotate from here to here, we're going to have to go through an eclipsed conformation. Maybe we'll call it eclipsed 1. And that eclipse conformation is going to involve a methyl group in the front overlapping with a hydrogen in the back, and a hydrogen in the front overlapping with a methyl group in the back. Right? And that should be higher in energy than either the anti-conformation or the gauche conformations. As to how higher in energy it should be, who knows? But let's put it, and there are numbers on this, but we don't care about the numbers, just the trends. Okay? Now, what about the eclipsed conformation in going from gauche 1 to gauche 2? What's that going to involve? Methyl eclipsedness, right? Which ought to be really bad, because now the methyl groups are not a little bit offset, now they're right on top of each other. And so, yeah, we would expect this one to be even less stable than the eclipse conformation we just drew. The letter Y got excited and thought it was coming with us. Too bad. All right, so, and in terms of how much more unstable is it, not sure. We don't care about memorizing numbers anyway, but the idea here is that methyl eclipsed is worse than methyl hydrogen eclipsed. So if we sort of start to draw this energy diagram and think about how energy varies, we have to go through a high energy barrier to get from anti to gauche. But to get from gauche 1 to gauche 2, you've got this eclipsed barrier. And then I suppose over here we have, that we didn't draw, we have another eclipsed conformation 3, that should also have methyl hydrogen eclipsed conformations, and so it should be at the same energy level as that. Since I have the awesome power of shrinking things, I guess we could complete our diagram. Complete with sound effects. Right, so going from gauche 2 to anti should require us to go through eclipsed conformation 3. That will be at this same energy level and is going to look like hydrogen, methyl, another hydrogen, methyl here, hydrogen there, hydrogen there. So yeah, same methyl hydrogen eclipsed interactions, and then we would continue on down the hill to get back to anti-conformation. All right? Why are we doing this? Well, think about this. If you were in the gauche 2 conformation, what is the lowest energy pathway to get to gauche 1? Is it to hike up the tallest mountain, or are you going to go the other way? Yeah, you're going to go the other way. You're going to go through the lower energy barrier. And this can have some interesting effects, but one of the conclusions you can make is that there would be some equilibrium distribution in solution of your gauche conformations and your anti-conformation. Now that depends on how much of each of these depends on how much energy we've got under whatever conditions we're doing an experiment. And the energy it requires to get over these barriers is indicated here, and your text will put numbers on it. We don't need to. But it turns out that if at whatever temperature you're at, the kinetic energy, the average kinetic energy of a molecule is higher than this barrier, then the molecules traverse the barrier freely without any trouble at all. The way you can tell how much kinetic energy you have at a particular temperature is to take actually the universal gas constant and temperature, and that will give you the energy in kcals per mole. If you wanted in just kilocalories per molecule, you could use Boltzmann's constant, KT. But you can plug your temperature into there and then see how big this number is relative to this barrier. And it just so happens that for us, in our world, at our temperature, there's enough energy for that to be rotating pretty freely and pretty constantly. I'll show... Oh, Among Us is open again. That's always fun. At home can't see the gallery of molecules, and I apologize for that because the refresh rate is not that great. I'm going to look at butane. We're looking down the central carbon-carbon bond. Notice that that is in the anti-conformation, right? Let's see if we can grab that methyl group and make it traverse the barrier between anti and one of the gauche. Okay, there we are. See how we fell into that well? Now that's not the most stable conformation, but we're staying in that well because at a bath temperature of 50 Kelvin, we haven't got enough energy to be freely rotating. Notice though, you can see that the methyl groups in the gauche conformation. Yeah, folks at home, I do realize that it's very glitchy, and I'm sorry about this. I've tried to find a good way to do it, but when I did it, it blurred out what you were seeing. So to see this, you will need to watch the video after the fact. And again, I am sorry about that. The methyl groups in the gauche conformation are pretty close to each other. Let's just turn up the temperature and see whether we can start traversing that barrier. Speed up the simulation. Jittery molecules. All right, there we go. It went anti for a while and then went back to gauche. So as we increase the temperature, yeah, we can start to see rotation around those bonds. Though it's interesting. I mean, we're getting a sense for the relative heights of these barriers. You're seeing that once we go from here to here, by applying some energy, actually you can sit around there for a while. Now, that's a single molecule in the gas phase, not surrounded by anything else. Of course, things are going to be different in solution where molecules are knocking into each other all the time, and that's going to cause translational kinetic energy to be imported into the molecule and cause things to rotate. So yeah, at room temperature, you have the ability to rotate around these bonds. But the idea that there might be a preferred arrangement of groups can be really important. What is the app called again? It's called Molecules. There's a lot of people on chat that are feeling very sad. Emma, Emma, do you want to type your question into the chat? I see your hand raised. Yes, you can use apps on tests. The app is Molecules by Theodore Gray. Okay, so now what would happen if you decided to put things other than methyl groups on these carbons? Then you would just simply need to consider all these various conformations and the relationship between them. So to answer that question, I think I'm going to copy this, paste it there, only I don't want any of this anymore. Let's just put one of the groups in the back. Let's have that be, I don't know, something like an OH group or something. And then let's modify another one of the atoms on the back to be a methyl group. And let's see what we think that does to the relative energies of the groups. I'm going to go ahead and make that change all the way around. The advantage here is that we no longer have to draw each of the Newman projections individually because we've copied them. I'm just filling in what the new groups on the back carbon are. One is an OH group and one is a CH3 group. And then we'll do that last of all here, OH and CH3. Okay, so let's just look.
You forgot the one just left, like the second one. The eclipsed one. Yeah.
Oh yeah, poor lonely eclipsed one all by itself. So we've set up the situation. It looks like we're out of time, so what I want you to do is to consider among the staggered conformations, which one should be lower, sort of rank them in energy, and among the eclipse conformations, which ones you think should be higher versus lower. I'll give you a hint. A methyl group is bigger than an OH group. And that may help guide your thinking. All right.